Well, I'm not quite sure how much I'll be able to cover in an hour, and I'll try not to rush through so as to cover lots of topics, and instead I'll attempt to give you some kind of qualitative explanation of the key ideas. So if I don't end up describing everything I intended to, but I do end up conveying some key ideas, then I will have succeeded.
Just do a tiny focus, please. Just a little bit out of focus.
And obviously you'll help me tremendously if you interrupt me by asking questions.
Thanks, that's much better. Yeah.
So that I get an idea of whether I'm connecting with you or not, particularly the students. If I take you back to some particular points in some of George's lectures, a number of questions about inflation, George made a lot of points about inflation, but I want to pick up, starting with two of the issues that were mentioned in the cosmology lectures. And that is to ask two questions about the data that we've been getting in modern cosmology. First of all, we could ask the question, why is the universe so flat? The data from WMAP and the Galaxy surveys and the supernovae observations tell us that the deviation of the total density parameter from 1 is bounded to be less than or the order of 0.05, which means that the universe is very close to a flat model. And that's a very surprising result, as we'll see in a bit more detail later on. It's something that needs some kind of explanation and accounting for. The second question, which is one which George did go into in some detail, so I will pick up again, but in less detail later on, is why is the universe so isotropic? And George explained this very nicely. If we look in one direction of the sky and then turn our instrument 180 degrees around to the opposite direction in the sky, we find the same temperature to within 1 part in 10 to the 5 once we've corrected for the Doppler effect. And that's an even more strikingly fine-tuned situation than the first one because the number is much smaller. The fluctuation in temperature is extremely small. And the reason it's so puzzling is because those two regions on opposite ends of the sky, from the viewpoint of ordinary cosmology, appear never to have been in contact with each other. So how did they manage to arrive at the same temperature without interacting with each other, without communicating? Now, there are two general ways of answering these two questions. There may be others, but these are the two that I'll focus on. Either we can just say, look, the universe is a special creature, or a special object, let me say, and its initial state is set up in some special way that we don't understand, but that's the way it is, and that's just it. The other way is to say, let's suppose that the initial state of the universe was as messy as you like, in a sense, some sort of chaotic state, as much mess as you like in the initial universe, as unsmooth and unordered as you like. Can we find a mechanism which will take us from that initial chaotic or messy state and, on one hand, smooth out the universe so as to explain why it's so flat by making it appear smooth and flat, and on the other hand, at the same time, hopefully, to establish some means of causal contact between these regions which appear to be so vastly separated from each other today. And if you think about such a mechanism, you'll see that it'll be required to achieve two things. First of all, the observable universe, which we see today, and that's of the order of 10 to the 4 megaparsecs, very large, will need to have been very, very much smaller at some early epoch, and it potentially could have been very messy at that time as opposed to relatively smooth and ordered today. And secondly, if you think about having to smooth out such a universe, you'll realize that you're going to have a lot of a lot of expansion in a short time. In other words, from a qualitative point of view, you may be led, if you were very perceptive, from these two questions to the idea that you would require an early epoch of accelerated expansion, which has been dubbed inflation in the universe. And it turns out that this is actually what happens. A qualitative guess at what you might need turns out to be true. But before just showing in outline how that works, I need to pause because those two questions are not the end of the big questions. Obviously, there are many other big questions which I'm ignoring. But an associated big question is, having solved those two questions, supposing we can answer those two questions, we have an even bigger question to answer. And that is, how did the galaxies happen to emerge in this scenario? Again, you can have two responses to this question. Either we have very special initial conditions in the perturbations. By perturbations, I mean fluctuations or ripples. You've got some smooth background and you introduce some ripples on it. Then you can, as George explained, understand that those ripples, the overdensities in those ripples, will grow under gravitational attraction and eventually form the galaxies. So either the initial state of the universe is set up in such a way that there are ripples imprinted right from the start by some mechanism we just don't understand, but it's given for all time from the start. Or we have a mechanism that will actually generate these perturbations in some natural way so that you don't have to put them in by hand. And the most remarkable thing that we could say about inflation really is the following. The same scalar field, which is something I'll describe a little bit later, which drives this inflationary expansion in the early universe so that it solves the flatness problem and the horizon problem, that same scalar field also naturally experiences quantum fluctuations. Because it's a quantum field in a curved spacetime, it cannot avoid actually experiencing quantum fluctuations. You can't stop them, and they naturally emerge, and in a very striking way, these fluctuations are exactly what can seed the perturbations that lead to the formation of galaxies. So that is the great triumph of the inflationary paradigm, is that it simultaneously answers questions about the dynamical background, why is the universe flat, how do you solve the horizon problem, and answers questions about structure formation. And that is what is so powerful about inflation, and also why it has been so difficult for people to come up with alternatives to inflation. And one can really say that up to now there is no alternative to inflation which can do those two things. No real alternative. So the basic idea here in the green symbols at the bottom, the fluctuations in the scalar field, which is driving in accelerated expansion, will be transferred into fluctuations in the metric, because if you mess around with the matter on the right-hand side of field equations, you're going to affect the geometry on the left-hand side. And, of course, by the same token, through the Einstein field equations, these fluctuations will then be transferred to the energy-momentum tensor at later times, which is not just a scalar field, because we know we must end up with radiation and cold dark matter and baryons. So there are going to be fluctuations imprinted in all those forms of matter. And eventually, at the time of last scattering, when large-scale structure and the CMB are being crucially, the initial conditions are crucially laid down, these will emerge as fluctuations in the density and the temperature. So this is the basic idea. So those two slides really try to summarize the key concepts involved in the inflationary paradigm. I don't call it a theory because, as George pointed out, at the end of the day, once we've gone through all of the analysis, if we ask the question, is there a fundamental particle physics theory which tells us how this could have happened or what the scalar field is, the answer is no, not yet. So it's not yet a proper theory, a fundamental theory. It's really a framework or a paradigm which is waiting for something more fundamental to either replace it or explain how it occurs. So I need to, in order to go through and flesh out some of those points, I need to just take you back to bits and pieces that were covered by George, that we can remind ourselves. Of course, the very first thing that I've got up there is the most fundamental dynamical object of all. It's the Friedmann equation, where for rho I've just used the total energy density, and K is the curvature. G is Newton's constant, which is 1 over the Planck mass squared, which is a useful thing to remember. And if we divide this Friedmann equation through by h squared to normalize it, we get the total density parameter minus 1 is given by the curvature over a squared, h squared. So as I was saying, rho is the total energy density. There could be radiation, matter, vacuum energy density, other forms of energy density. The energy momentum tensor would similarly be made up of radiation plus matter plus vacuum. And if you look at the Einstein field equations, the vacuum contribution from the cosmological constant is just minus lambda over 8 pi g times the metric. Now, you'll also know that in a Robertson-Walker metric, you can express the energy-momentum tensor in the form rho plus p times u mu u nu, where u is the fundamental fall velocity of co-moving observers, plus the pressure times the metric. And each of these energy-momentum tensors will be of this form, provided the components of energy density are not interacting with each other, which is true for most epochs in the universe. And if you compare this with that, you will see quickly that for the vacuum, the pressure of the vacuum is minus the energy density. And the energy density is just basically the cosmological constant normalized by 8 pi g. We already know that for radiation, the pressure is a third the energy density. For matter, cold dark matter and baryons, after matter radiation equality, the pressure is effectively zero. So we use this W parameter, which is simply defined as the pressure divided by the energy density. It's the same as George's gamma minus 1, where gamma is George's parameter. I'm going to use W. For the vacuum, of course, W is minus 1. That corresponds to the case of a cosmological constant. You also saw the other field equation, which relates the second derivative of the scale factor to the right-hand side to the energy momentum tensor, and namely A double dot over A is minus 4 pi g over 3 into rho plus 3p, where this is the total rho and the total p. So I can write that as minus 4 pi g over 3 rho times 1 plus 3w, where w is just the total equation of state parameter. The energy conservation equation is something you're also familiar with, and of course you know that if you take the Friedmann equation and the energy conservation equation, you can derive the Green equation. So these three equations, these two plus that one, are not independent. There's two independent equations. Now, if you assume that W is a constant, and that at some time period in the history of the universe is dominated by one fluid with a particular W, you can use these equations in the case where k is 0, taking out the curvature there, to show that the energy density, the Hubble rate, and the scale factor are given by these simple expressions. So I'm not going to need the details. I won't need you to remember those details. Just when I need these results, I'll come back to them. But essentially, one can, as an exercise, if you haven't done it before, that's a good exercise just to show that you can derive those equations over there. Another basic thing that we will need that George discussed is the conformal time. George described this in the context of Penrose diagrams. They're very useful for understanding causal relations in the universe. So if we change the time coordinate by rewriting the metric in this form here, where tau is dt over the integral of dt over a, then we can rewrite those solutions in the following form. The conformal time tau is some constant times the proper time t to this particular power. And the key thing to notice here is just the crucial values w equals minus 1 and w equals minus a third, where things obviously are critical. And we'll see that shortly. And in terms of the conformal time, the scale factor can be written as the absolute value of tau, because tau turns out to often be negative in the history of the universe. The absolute value of tau to this particular power over here, minus 2 over 1 plus 3w. I won't go back to the previous slide, but something which I didn't mention that was obvious from it is that the acceleration of the scale factor is positive if and only if 1 plus 3w is negative. And conversely, if we're in either matter era or radiation era, where w is definitely greater than or equal to 0, a double dot will be negative, so the universe is decelerating. So again, this value of 1 plus of w is minus a third is the critical value. That really comes from the a double dot equation, and it crops up in these solutions because it's in the A double dot equation. And finally, in terms of background facts that we will need, if we think about the special case of the de Sitter universe, this is the solution when k equals 0 and you have only a cosmological constant, a positive cosmological constant, so that W is minus 1. It's not difficult to show, and you should do this if you haven't as an exercise, that the solution to the field equations is that A is exponential, and the Hubble rate h is a constant, just determined by the cosmological constant. The conformal time is given by minus 1 over AH. So you can see that in a de Sitter universe, the conformal time is actually negative. It's increasing, but it's negative during the expansion. So it's a very simple but a very important solution, as we'll see later on, because essentially the inflationary models are a slight perturbation. Most inflationary models are a slight perturbation of this de Sitter, a slight deformation of the de Sitter, as I'll describe later on. Are there any questions so far? Is anybody puzzled about any of the things I've said or want me to explain anything further? Please ask me, yes.
If de Sitter's space-time is static, then how can it describe something which is inflating?
Well, if it's not exactly de Sitter. Okay.
I've got a question on your second slide, your quantum perturbations. Can I do that?
Second slide starting from what? From the beginning.
Where does h bar come in? The equations follow.
H bar is 1.
Yeah, but you have all these various things which you're perturbing. Not clear quite where, if you're going to put it back in, where we're going back in.
You mean this slide here?
Yeah, at the bottom. So,
Well, there's an issue of how quantum fluctuations become classical, which is something I was going to either ignore or delay until the end. But since you've raised it, quantum fluctuations are generated in a quantum way, but because of the dynamics of inflation itself, which stretches these fluctuations outside of causal communication, roughly speaking, they become classical, they become frozen. And well, H cross actually comes into the Planck mass, and you don't see it in my formulae because I've set it to 1, along with the speed of light. But perhaps we should leave that question to later. You can make it more concrete. So let me just remind you, I've posed these 3 questions about the universe and given some qualitative hand-waving answers to why we may expect that an accelerated expansion phase driven by a scalar field may answer these questions. I've just taken a detour to remind you of some dynamical facts and geometrical facts. Now let's come back to see how the answers to those 3 questions actually turn out to work. So let's come back to the first question. Why is the universe so flat? So if we write the Friedmann equation in normalized form, the difference between the total density parameter and 1 in magnitude is given by the magnitude of the curvature parameter over a squared h squared. And this evolves roughly like a to the power 1 plus 3w. Now, what that means is that this quantity 1 over AH is growing as long as W is greater than minus a third, which includes the standard cases of radiation and matter-dominated eras in the universe. And George actually showed you some phase diagrams in which it was clear how the difference between omega and 1, either positive or negative in both cases, grew dramatically with the expansion of the universe. And this is certainly true, provided the universe is dominated by a fluid with W greater than minus a third, that the difference between omega and 1 is going to grow with expansion. Now, observations tell us that today the difference is very small. So if we run time backwards, thinking that we've got W greater than minus a third, which is all the ordinary matter we know about certainly satisfies, we find that omega minus 1 has to be extraordinarily small at earlier and earlier times in order to end up being less than 5.05 today. And that's the flatness problem. So in fact, if at early times, at some early time Ti, the relationship between omega minus 1 at ti and omega minus 1 at t naught, i.e. now, is determined by this factor a naught over ai to the minus 1 plus 3w. So, for example, if we go back to nucleosynthesis, which happens in the radiation era, I can just, for an approximation here, I'm ignoring the matter-dominated era, just assuming the universe is radiation-dominated for all time. It only makes a small difference to do it exactly. It turns out the redshift of nucleosynthesis is about 300 million. And that means that this factor a naught over ai, where I is now an, the time of nucleosynthesis, is about 3 times 10 to the 8. And so we need the density parameters difference from 1 to be bounded by about 10 to the minus 16 at the time of nucleosynthesis, as an illustration of what I was saying. If we go earlier back in time to the electroweak transition or to the gut transition, we're going to get even more severe fine-tunings, even smaller numbers. But the way out, the way to escape from this bootstrap, if you like, is to break this condition here, w is greater than minus a third. If we break that condition, then it turns out that the factor 1 over ah, which is going to, as we'll see, turn out to be a very crucial quantity in our analysis, is actually decreasing. So for ordinary matter and radiation, 1 over ah is an increasing quantity with expansion. But if there's a period in the early universe where this quantity decreases, then we can get out of this flatness problem. And of course, you can see that the condition, namely that w is less than minus a third, is exactly the condition for the universe to be accelerating. So we need an accelerated expansion as a basic condition to solve the flatness problem. Without that, we're not going to be able to solve it. In fact, I should point out that one can go deeper into this, and if one is more careful about the various epochs of the universe's history, one can actually start characterizing some of the basic properties of the length of this expansion epoch, of this acceleration inflation era that one needs in order to solve the flatness problem. But I don't have time to do that. All I've shown you is that we certainly need a double dot positive to get out of that problem of trying to explain why the universe appears to be so flat. If we do have this accelerating expansion era, then there will be a time in the early universe when omega is driven towards 1, so that we don't have to explain why it is so small at early times. Now, before moving on to the second question about why the universe is so isotropic, I need to just pause and say something about scales in the expanding universe, physical length scales, and similarly one could talk about time scales because length equals time for us relativists if we set the speed of light to 1. If we consider some physical scale lambda, it could be the wavelength of some mode, it could be some physically defined length, as I'll mention some examples later on, but any physical scale lambda, due to the expansion of the universe, is stretched by that same expansion. And so it's stretched by a factor exactly proportional to the scale factor A. So distances between points are stretched by a factor proportional to the scale factor. And the normalization of such a physical scale, we can do it in terms of a quantity 1 over k, which I've done here. And we're doing that simply because this then sets up a relationship wavelength, wave number, which we're quite used to. So 1 over k is the co-moving wave number. It's a fixed quantity which normalizes that physical scale. It doesn't change with the expansion of the universe, but it tells you what the actual size of the physical scale is. Once you know k, then you can tell how it's stretched by expansion because it's just proportional to A. Alternatively, you can think in terms of a co-moving wavelength. The co-moving wavelength is the fixed scale which normalizes the physical wavelength lambda. It scales with expansion by A, and the co-moving wavelength is just 1 over the co-moving wave number, K. And this, the use of K is suggestive because we often need to break things into Fourier modes. When we're going to look at perturbations or fluctuations in things, these are quantities which are not smooth anymore, and we're going to have to decompose them into Fourier modes. So it's quite useful to use the notation k here, because it's exactly the same k that crops up in Fourier modes. So if we want to analyze a function which depends on the spatial coordinates x, y, and z, we would decompose it into its Fourier transform, a function f tilde which depends on the wave vector k in the usual way for a Fourier transform. So f of x is the integral d3k over 2 pi cubed e to the I k dot x times f tilde of k. Since I'm doing lots of hand waving and I don't want to clutter up my slides too much, I'm actually ignoring factors of 2 pi. I should strictly have a 2 pi in there, but I'm not going to bother with 2 pi's if you don't mind. For each Fourier mode, the actual length of the Fourier vector k, this k here, is exactly the co-moving wave number of the associated wavelength of that mode. So this definition here exactly works out, and it's why the notation is so useful, because it's very much consistent with the Fourier analysis. But there are also other scales, and two of them were described in some detail by George. Let me just remind you about them. First of all, there's the Hubble radius. The rate of expansion of the universe h, which has dimensions 1 over time, defines a length scale or a time scale via its inverse, 1 over h. And this is a physical scale, lambda h. It's sometimes called the scale of the Hubble horizon, and people get a bit sloppy and they talk about the horizon, but we have to be very careful that this is not the horizon in the sense that George explained as well, which is the particle horizon. You could call it the Hubble horizon if you like, but I'll try to stick to calling it the Hubble radius. And of course, this thing is time dependent, and the co-moving version of the Hubble radius, of the Hubble scale, the lambda h co-moving, is just 1 over a times this, by this definition above, so it's 1 over ah. So as I said earlier, this quantity 1 over ah is a key quantity. It's just the co-moving Hubble radius in the universe. So it's the normalization, it's the fixed scale which corresponds, not the fixed scale rather, it's the co-moving scale which corresponds to the Hubble radius in the expanding universe. The particle horizon, on the other hand, as defined by George, and I can't go through this in detail because I don't have time, but it was gone through in quite a lot of detail by George, and it's in the notes that George handed out. This is given by the scale factor a times the integral from 0 to t of dt prime over a of t prime, and the co-moving particle horizon you just divide by a, so it's just this integral, which is the conformal time, essentially.
Why the universe is flat? We asked the question. Now, I don't have any problem with the isotropy of the universe. But what do we mean by the universe being flat? What do we mean? Now, we have our own planet, we have a solar system, we have a galaxies. Does it mean all these bodies are on the same plane, or what does it mean for the universe to be flat?
No, and in fact, you're raising a good question there, because if we look on the scale of the solar system, or on the scale of the planet, clearly things are not flat and smooth. There are all sorts of nonlinear structures. So really I should be a bit more precise and say that the universe on large enough scales is flat. So if we go to scales where we're treating not only galaxies but clusters of galaxies as if they were particles without looking inside them, and we do that in most of cosmology, if we go to those kind of scales where we don't worry about small details, if you know what I mean, then the universe, on average, is very close to being flat. But more precisely speaking, flatness of the universe is determined by the size of this quantity. This is a dimensionless quantity. It's the magnitude of the curvature parameter of the Robertson-Walker model underlying the universe, divided by a squared h squared. And if this thing is small, then the universe is nearly flat. Of course, we have the special case if we choose the exactly flat Robertson-Walker model where k is exactly 0, then this thing is guaranteed to be small at 0. It's exactly flat. But I'm not making that choice. And this was another thing that was discussed by George, so perhaps look in those notes as well for a bit more discussion of the difference between an exactly flat universe and the smallness of the curvature at different epochs in the history of the universe. They're not the same thing. I don't know did I answer that question?
It might be worth reminding the picture people like to have in mind about the three different values of k.
Yes.
The plane, the sphere, and the hyperboloid. It might be worth having those pictures just to remind people.
Okay, yes, that's a good point. Thanks, Clifford. So a k equals naught. If I freeze time in a Robertson-Walker universe, and I take a slice at some constant time, then I've just got space, 3 space coordinates, at any time in the history of the universe. Now, in a k equals naught Robertson-Walker model, such a slice would be Euclidean space. It would be flat. So I've drawn it as a 2 surface here because I can't draw a 3-dimensional surface on the blackboard. I'm suppressing one of the coordinates. The k equals plus 1 model, by contrast, would be the surface of a 3-sphere, which I'm drawing as the surface of a 2-sphere because I can't draw a 3-sphere. So this would be what's called a closed model because it clearly closes up on itself. This is an infinite model. It carries on. You can move in any direction for an infinite distance without ever coming back to something that you previously went to, whereas in this model here, if you went all the way around the universe, you'd come back to where you started eventually. So it's a very different geometry. It's actually closed. And the open models, or the hyperbolic models, these are the ones which I can't really draw. Something like a saddle. You've got to sort of think. If you think of a saddle on a horse, it's shaped like a saddle. And the key thing is that if you draw a triangle here, the angles add up to 180 degrees. If you draw a triangle here, the angles add up to greater than 180 degrees. If you draw a triangle here, the angles add up to less than 180 degrees. So it's one way of understanding how radically different these geometries can be. But the point I'm making about this quantity here is that if the universe is expanded for long enough, as it has today, it's been expanding for nearly 15,000 million years, even if the universe is a k equals plus 1 geometry, that 3-sphere would have been expanded to a huge size. And so that the patch that we can see, which is sort of, say, a little patch like that, appears almost flat. So that's the key idea. But if we run it backwards in time, and we go to earlier and earlier times, the curvature term will become more and more significant. And in the very early universe, the curvature term will typically actually dominate, so that you can't get around the fact that you really are in a closed model. Okay. Now, if I come back to this idea of the scales, I've spoken about physical scales, and in particular the Hubble radius and the particle horizon and Fourier modes, all three of which are crucial for what we need to do in the subsequent discussion. Let's just say something more about the Hubble radius. Now, h tells you how fast the universe is expanding, and you can show by a quick calculation that the expansion time of the universe is typically a time in which the scale factor roughly doubles. And h inverse then can be understood to be the distance which light can travel in an expansion time. So what you have to think about in the universe is, suppose I have a particle, I'm sitting on a particle which is this black dot here, and I'm considering a sea of other particles around me. They could be galaxies in the late universe, or they could be fundamental particles in the early universe. there are two different kinds of particles, the green ones and the blue ones. The green ones are the ones with which I can at that time communicate through light signals or other propagating particles, and the blue ones are the ones with which I cannot at that time communicate. Because the blue ones happen to be outside my Hubble radius, they're further away than the light travel distance in an expansion time. Because as I'm looking at these particles, we're all being stretched away from each other by the expansion of the universe. And so there's some particles which are too far away for me to communicate with within an expansion time, and there's others which I can communicate with. Obviously, the particle right next to me, or I myself, I can obviously always communicate with. But the particles that I can or cannot communicate with at any given epoch in the universe are determined by the Hubble radius, or the Hubble sphere, if you like, at that time. This red circle here is really a sphere in 3 dimensions surrounding the observer, or the particle you're thinking of. And it's important that I'm talking about current causal interaction. This doesn't mean that I could never have communicated with that particle. It may be that in the past of the universe, when things were different, I did have contact with that particle. And in fact, this is exactly how we resolve the horizon problem or the isotropy problem. So to summarize, I've said here, if a distance or a scale is greater than the Hubble radius, then there's no communication possible between the center of the sphere and the other end of that scale at that time. However, if a scale is greater than the particle horizon, then at the ends of that scale, it's never been possible to communicate. So those two particles at the end, either end there, can never have communicated. This was also explained very nicely by George in his Penrose diagram of the history of the universe, which I'll come back to later. It's clear, therefore, that scales can actually cross the Hubble radius, but they cannot cross the horizon. If they're inside the particle horizon at one time, they're always inside. And conversely, if they're outside at one time, they're always outside. But there's no law which stops a scale from crossing the Hubble radius. That's a different matter, because the Hubble radius is changing depending on how the universe is expanding, which depends in turn on what energy density you have on the right-hand side of the field equations. So with those points about scales in mind, let's now come back to question number 2. How did the CMB isotropize? How was it that that end of the sky and the exact opposite end of the sky happened to be at more or less the same temperature when all our standard calculations based on the standard model of radiation and matter tell us that that region and that region can never have communicated with each other? Well, in order to be able to explain this isotropy, we have to have the following situation. It has to be true that in the past, the currently observed universe, which contains regions which appear never to have been in contact, and certainly currently are not in causal contact, were in fact in causal contact at some early time. In other words, the currently observed universe was at some time within a Hubble radius, early in the universe. Now, this is impossible, as George showed, if you only have matter or radiation in the universe. It is only possible to have this situation if there is a period of accelerated expansion. So what is actually happening here is that for most of the history of the universe, for nearly all of the 14.7 billion years of the universe's history, there is no causal contact between these regions that we're looking at in the sky. But in the very early part of the universe, for a very short time, they actually were in causal contact. And therefore, they had a chance to communicate and establish a common temperature to within quantum fluctuations. So let's try and unpack that a little bit. I don't want to repeat George's conformal diagram, which was very nice, so I'll do an alternative diagram for you, which is the non-conformal diagram. Here is the last scattering surface, or the decoupling, time of decoupling. Here is the current time of observation. There's the time at the end of inflation. The blue lines are just the past light cone, so the light is traveling up from the last scattering surface when photons free streamed to reach us. This is the observable universe now, this huge Hubble sphere of radius about 10,000 megaparsecs, roughly. If we take back the observable universe, running the expansion of the universe backwards, what we're saying is that we can't solve the problem if we don't have an accelerated expansion. George explained this. You can show that it's impossible for this region here to ever have been in causal contact if you just have radiation in the past. But if we have this accelerated expansion, it allows the possibility that a very small region, something which was less than a Hubble radius or within a Hubble radius, and therefore was in causal contact at some early time, was blown up super rapidly by an accelerated expansion to become large and therefore to evolve into the currently observable universe. And this really is the basic idea. You need that super fast acceleration to turn a small region which you need for causal contact into a big region which we observe today. That solves the problem of why the sky is so isotropic. So it's those basic ingredients. I'll try and make it a little bit more precise in the next two slides, but this really is the key idea. We have to take back the observable universe, which is huge, to a past point where it was very small, small enough so that it could have communicated by light rays and other particle interactions so that it could have established a common temperature. And the only way we can do that is if we had a very super fast period of expansion to blow this very tiny thing that we need for causality into a large enough universe that we observe today. That's really the key. That's all there is to the solution in one sense. It actually turns out, and if you look at textbooks, and I'll talk about some reading later at the end, which seems to be not that far away, it turns out that in order to solve the isotropy problem and the flatness problem, the inflationary period we're talking about needs to have a certain length, needs to go on for a certain length of time, and the length of time you need to solve the two problems are very much comparable. So that's also a very nice part of the solution of these two questions. It may have been that you solve the one problem with one kind of inflation and you solve the other problem with another kind, and the two things are incompatible. You need long inflation for one solution and short for the other. That would have been the end of the inflationary models because they couldn't have answered both questions.
At some stage in that rapid acceleration, are there bodies which are moving apart from each other faster than the speed of light? They would have to be.
Yes.
And
it's superluminal expansion in a sense. Yeah.
So does that avoid problems with relativity? Because
there's no problem with relativity.
How does that work?
Well, you can attach yourself to a co-moving a fundamental observer, and relative to that observer, you can work out speeds. But there's no causality violation. I mean, this is quite tricky to do. There's a very nice paper by George and Bill Stuger, and a more recent paper by Charlie Lineweaver and Tamara Davis. If you look on the web under Lineweaver and Davis, or Davis and Lineweaver, and they'll have a reference to George's paper with Stoger. There's a very nice discussion of the various horizons and the Hubble radius and the visual horizon and the particle horizon, and a very nice discussion about speeds of separation between points and about the maintenance of causality. I don't have time to try and give you a qualitative description of that now because that would take me another 10 minutes. But we might discuss that again a bit later. But have a look, Lineweaver and Davis, 2002 possibly. Check on the archive, you'll find it quite easily, and then a reference to George's paper as well. So causality is not violated, even though it's, in some senses, this is superluminal expansion in a loose sense.
Well, you should bear in mind that we can start at, so for the purposes of planning the rest of what you want to say, I think you can go to about 10 past, including questions.
Okay, right. So I don't want to rush, so...
But Roy, very briefly, inner surface T is constant. Galaxies within a certain time are expanding at less than the speed of light from us, and outside they're expanding faster than the speed of light at any instant because it's an infinite flat space section. But there's no
we can't communicate with it.
We can't communicate.
Okay, so maybe it's quite easy to have said that. Thanks, George. The ones that are going away faster than the speed of light we can't communicate with, so there's no violation of causality. And all these speeds are measured relative to fundamental observers. It's another thing that one has to bear in mind. Now, to come back to this isotropy issue, let me put it another way. It turns out I think this is more useful to think of this in terms of co-moving scales. You can do it either way, in terms of physical scales, which was the previous diagram, in terms of conformal diagrams, which is something that George discussed, or in terms of co-moving scales, which I find quite useful. The statement is the following, that in the co-moving Hubble ray sphere at the current time, the particles, i.e. galaxies, etc., must have been in causal contact at some much earlier time. So in other words, the co-moving Hubble radius at the earlier time should be at least as big as the co-moving Hubble radius now. Because this co-moving Hubble radius has factored out the expansion, we don't have to go through this nonlinear bottle-type shape that we had on the previous diagram. We can think in terms of co-moving scales, the fundamental scales. And now we can come back to what we know about this co-moving scale. We know that the co-moving Hubble radius grows during matter and radiation eras. As we saw, just to remind you, during the radiation era, AH inverse goes something like A, and during the matter era, I think it goes something like A to the half. It's growing with expansion, getting bigger and bigger and bigger. So, of course, if I run this backwards in time and nothing else ever happens, then I can never get this to work, because I'll never get an earlier time when the co-moving Hubble radius is as big as the final one. I have to have a period where AH inverse decreases. But we already know that inflation does that for us. If we assume that inflation is taking place so that it's nearly de Sitter, which is the simplest kind of an accelerating solution, then we would have that the scale factor is nearly exponential, and this with h being nearly constant, and this means that the co-moving scale in inflation is roughly 1 over a, which is clearly decreasing. So if I use that approximation, which is a very good approximation for most standard models of inflation, then I come up with a following diagram, which I think is quite useful. See if you agree with me. Looks like I'm going to have to end not too much further on than this, but because I'd like to spend a bit of time discussing the details of this diagram. What I've mapped here on logarithmic scales is co-moving distances of various kinds in megaparsecs. That's 10 to the 4, 1, 10 to the minus 20, I think that is there, against the scale factor of the universe, also on a logarithmic scale. There's AI, 10 to the minus 40, 10 to the minus 28, 10 to the minus 4, and 1. The red line gives me the co-moving Hubble radius. During inflation, it is decreasing. So it's going like 1 over a, so on a log scale, it's just a straight line, approximately. During the radiation-dominated era, it's increasing like a, so on a log scale, it's going like a straight line with slope 1. Then you get matter taking over, so it starts going like a straight line with slope a half, and it'll start, as the cosmological constant starts to dominate, there's going to be another period of inflation, so it actually starts dropping here. I ran out of space here, but it's going to start dropping here again, but we'll forget about that for the moment. Now the point is the following. The scales which affect large-scale structure, i.e. the formation of galaxies, are of the order of a megaparsec and over. You can go a bit below a megaparsec, but if you want to talk about galaxies and clusters of galaxies, if you want to look at the anisotropies in the CMB out to L values of 1 or 2 or 3,000 or so, you're talking about scales in this band here, up to the current Hubble scale of 10 to the 4, and down to about 1 or a bit less than 1. So these scales, and these scales are represented as constants because these are Fourier modes co-moving and therefore constant, they don't change at all in time, you can see that the scales that were inside the Hubble radius at early times have come back inside the Hubble radius again at late times to seed the growth of galaxies. And we can also at the same time see that what's apparently not in causal contact over here was previously in causal contact over there, because it was previously, everything that we see today in the universe here was previously inside a Hubble volume where it could have established communication, thermalization, and so on. In order to make the transition from inflation to radiation, we have to go through a reheating period. Remember that the temperature of the universe goes like 1 over the scale factor. During inflation, this is being driven rapidly to 0 because the scale factor is growing like an exponential, so 1 over the scale factor is going like e to the minus ht. Inflation supercools the universe. It brings it down to near 0 temperature. We know that the universe must have been hot because we know the nucleosynthesis happened, and that's at a temperature of about 10 to the 8, and even higher temperatures we know must have existed. So we have to have some mechanism, and I'll talk about that if I have time, to reheat the universe and bring us back into a hot Big Bang radiation-dominated model. So there is a reheating process, and the inflationary models do take care of this, although there are lots of complications and details and interesting particle physics going on there, which is quite messy, and I won't have time to discuss. But essentially, this picture then conveys both the dynamical background situation where things that appear to be out of causal contact today were actually inside causal contact very early on because of inflation. And secondly, it also starts to answer the question number 3, which I'm not going to have time to really go into. But that is, if we start to generate Fourier modes of perturbations inside the Hubble radius during inflation, then they get stretched by expansion. You don't see the stretching here because I'm doing only co-moving scales. And eventually, they will come back inside the Hubble radius at late times, where they can start causing fluctuations. Because now, again, they start to have a causal effect inside the Hubble radius. And so, essentially, inflation then will also, because inflation is generating these perturbations, you can also see that the modes the Fourier modes which we're talking about can actually come inside the Hubble radius and cause the anisotropies in the CMB and the growth of galaxies that we observe. Of course, there are lots of complicated details that I would need to go into to unravel that statement of mine. I'm waving my hand a lot here, but there is a lot of detail that I'm having to skip over. But I'd rather just wave my hands than throw lots of equations at you. I do have, according to Clifford, 5 minutes left. And perhaps if you'll allow me, I could just quickly say a few more things, because it's a bit of a bad place just to leave you hanging in the air. I want just to close off how to get this accelerated expansion. As I said, we need a scalar field. Well, you've done some particle physics. You may already have come across this. At very high energies in the universe, we may expect that quantum fields would be dominant rather than radiation and matter. And the simplest quantum field is a scalar field, so let's have a look at it. It has a Lagrangian density. If you don't know what that is, don't worry about it, but you may have come across that in some of the other lectures, given by gradients of the scalar field and the potential of the field. So the potential of the field governs how the field evolves dynamically. The energy momentum tensor you can work out from the Lagrangian, and from that, as an exercise for maybe the workshop week in the school, I could set this problem for you. From here you can work out the energy density of a scalar field and its pressure. And this is the key formula here, which George has also mentioned. You get the kinetic energy plus the potential energy here, and the kinetic energy minus the potential energy there. And clearly, if the kinetic energy is much less than the potential, follows from the black box that P is nearly equal to minus rho, so W is nearly minus 1. In other words, we have acceleration, and we will have actually A is nearly exponential with H nearly constant, because W is nearly de Sitter, nearly minus 1. And that's all you need. If you've got a quantum scalar field, all you need is the potential to dominate. So suppose the potential looks like this. If I'm there, the potential certainly dominates because phi dot squared is 0. So there you'll have inflation. If I'm rolling down certain parts of this potential, provided it's not too steep, you could easily have this also happening. So as long as the derivatives of the potential are small, you're going to have these conditions as well happening. So it's not difficult to get accelerated expansion from a scalar field. Sorry, I don't mean you to sort of absorb all the details there, but just the ideas. And those of you who are writing, I apologize because I'm just trying to pop up my last transparency. It's easy, and I'll give this also as an exercise to derive the dynamical equation for the scalar field from the energy conservation equation. It's called the Klein-Gordon equation. We know the Friedmann equation, and I've just replaced rho by the rho of a scalar field. Now, if the scalar field is slow rolling, in other words, if we're nearly like de Sitter, then I can neglect that phi double dot and I can neglect that phi dot squared, and things become much simpler. The simplest potential example is this quadratic potential, and I could just end off by saying this is what happens in this simple model. The scalar field starts quite high up this potential. Potential has to be quite flat, so m has to be pretty small so that it's not too steep. In other words, the potential in the beginning, it must be much bigger than the kinetic energy density. The scalar field starts rolling down. Round about here, where we're first interested in the scalar field, is where the quadrupole in the microwave background is generated. At earlier times, for higher values of phi, scales are generated which are not yet coming inside our horizon, so we haven't yet measured them. But at least we have measured the quadrupole, so we need to know where that is. Eventually, as this scalar field rolls down, it reaches a point where v equals phi dot squares, because it's picking up speed here. It's picking up speed as it rolls down. So eventually, this condition is going to be broken, and v will equal phi dot squared. Acceleration will stop. It will start to decelerate. This is the end of inflation over here. Then it reaches the bottom, but it's got too much speed to stop at the bottom in equilibrium. It's going to oscillate. It will oscillate according to this equation here. You can see v prime is proportional to phi. I can't neglect phi double dot anymore because I'm not slow rolling. So I have a damped simple harmonic oscillator, damped by expansion. And during these oscillations, what's actually happening is the energy density in the scalar field is being converted to radiation. This is the reheating that's going on. So that, in a nutshell, is the picture that I've been talking about. Unfortunately, I haven't had time to give you a qualitative description of how the perturbations are generated. I've mentioned these Fourier modes, and I've mentioned these fluctuations in the scalar field, but I simply haven't had time to try to give you an idea of where they come from and how they behave. And I'd rather not try and do that in 30 seconds. You just have to leave it. I can refer you to books where you can pick up further details about this. And in fact, maybe I should end up with recommending that a good place to look for further reading on inflation is the textbook by Liddell and Lythe. I think it's 2001. And it's probably called something like Cosmological Inflation and Large-Scale Structure. Or words to that effect. I can't quite remember now. It is quite technical, but there's a lot of detail in there, and you could really choose your level. There's some references to more simple text and to more advanced text as well, and depending on how much you wanted to go into inflation, that's a good starting point. Right. I think I'm just on time when I see Clifford is there to confirm the fact that in fact, I'm afraid I've finished without time for questions, but perhaps if anyone has a question, we could go in a couple more minutes.
Yeah, so please, this is a good time to ask some questions. Make sure you all have the central point locked into your brain. If not, this is a good time to ask questions to help it along. And it's worth sacrificing some coffee time for that.
As I said, just to remind you, I will make a list of exercises based on some of the equations that I've been talking about, ask you to derive some of the formulae that I showed you and a few others perhaps, because that's a very good way of becoming familiar with the things I've spoken about. Until you actually calculate something, you don't understand it. Well, in fact, sorry, there are just two things I have to say. To understand bits of physics, or certainly bits of cosmology, you need two things. One, you need a hand-waving argument, which is based on scales and orders of magnitude and physical intuition. If you don't have that, start looking. And two, you need to do some calculations. You need both those things in order to get a rounded understanding. So I'll try to give you some hand-waving arguments. I hope I succeeded to some extent. And I'll give you some exercises to try and do some of those calculations to sharpen up that understanding. George?
The question is, does it matter what happened before inflation?
Yes, okay. So it does indeed matter what happened before inflation. It's something I've glossed over. If I had more time on the perturbation section, I was going to say something about that. But essentially, there are basically two ways to go. You can either assume that there's a radiation-dominated era before inflation, and before that there's a quantum gravity era, or you can assume that we emerge straight from the quantum gravity era into inflation. Well, there may be other variations as well. There are actually other variations. There are a whole plethora of models. And the problem is that the reason we can't really tie this down is the same as the reason that we can't find a fundamental framework to explain why inflation occurred, or to actually give us a potential V of phi or give us a scalar field phi. And that really is the fact that we don't have a quantum gravity theory. So as we try to push Einstein's field equations and quantum field theory further and further back in time, i.e. to higher and higher energies, we start running more dramatically into the limits of both of those theories, quantum field theory and general relativity. And since we don't have a quantum gravity theory, we have lots of guesses and semi-theories and ideas floating around, but no consensus and no emerging, clearly developing quantum gravity theory. We really are speculating. We're at the edge of speculation. But we're also at a place where some of these speculations are constrained by observations of the microwave background. So inflation itself is limited because things that are happening in inflation are being measured in the CMB. There are constraints from observations, but they're not tight enough to give us an answer. So really, in a nutshell, the answer to George's question is that it matters a lot what happened, but we haven't a clue what did actually happen. Yeah, I could say a lot more, but there's no more time.
Do you have any experimental evidence at all for inflation as you have for the Big Bang theory? Or is this purely speculative?
Well, the Big Bang theory's experimental evidence is archaeological. I mean, we measure we see the existence of elements in the stars and the galaxies, and we have a theory which can account for them, nucleosynthesis. But we also see galaxies, and inflation it's a semi-theory which can account for them. So we have indirect support for inflation, but we don't have verification now. The deeper question, is inflation falsifiable? Well, that's a more tricky question, because it's not really a full-fledged theory. It's a collection of theories sitting in a framework which we could call a paradigm, and because of the huge freedom there in this unknown potential V, which only has to satisfy various constraints, it's actually quite a difficult question to answer. You can choose particular potentials, and you can actually rule them out by current data. So, for example, the potential V goes like phi to the 4 is almost by now ruled out by current data. But then there's hundreds of other potentials which aren't ruled out. So it's not clear what the status of inflationary paradigm is as a falsifier. It may not be falsifiable. George might be able to say more about that. But I think it is also true that we don't have experimental verification of general relativity. We have good evidence that it works, because to get the nucleosynthesis in the way that with all the difficult coincidences of things that are being put together there, very strongly suggests that GR and quantum field theory are correct at nucleosynthesis energies, because it's very hard to see how else we could get that archaeological evidence, if you like. And there is strong support for inflation as well, because of the existence of galaxies and all the other issues I've discussed.
Any other questions?
it actually lasted for an extremely short time. So, again, time scales, when you look at them in absolute terms, it's a bit misleading. But the Planck time, which is the time after which, before which quantum gravity has to hold. In other words, this is the time, at earlier times, general relativity breaks down completely. But after the Planck time, general relativity will begin to be valid. So the Planck time is 10 to the minus 44 seconds. So we would think the start of inflation can't be before then, because otherwise we'd have to have quantum gravity. And we're looking at inflation with general relativity and quantum field theory. So the start of inflation must be greater than the Planck time. And the end of inflation, this depends a lot on the reheating process, which is very messy and complicated, and depends in particular on what the reheat temperature is. But typically, the time for the end of inflation would be less than or about the grand unified theory time, which is about 10 to the minus 32 seconds. And I mean, that's a very short time, even if you take the limits from one to the other. But it's long enough to do the trick.
How many e-folds are these?
Right, so there we need inflation to happen we need the end of inflation scale factor over the beginning of inflation scale factor to be greater than about e to the 60 in order to solve the horizon and flatness problems. Something I would have done if I had time, but I'll put it in these exercises. This can be worked out on the basis of all the things I was discussing today. So that's called 60 e-folds. That's about 10 to the 28, I think. But it's useful to think in terms of e-folds because the expansion is nearly exponential. So the universe is blowing up a huge amount in that very short time.
Okay, so I suggest that given that we're 15 minutes over, that we make sure that Roy also ends up near the tea and coffee, and then you can form a circle around him and ask him more questions with a cup of tea or coffee in hand, and continue discussing. So let's add about 15 minutes to the schedule. So we'll start the next particle theory lecture